Time is not a river that flows in one direction. It is a dimension, like length or width, woven into the very fabric of existence, and if we are honest, we must admit we understand far less of it than we pretend. I have spent my life chasing the hidden architecture of reality, searching for the equations that might explain why anything exists at all. And in this search, I have learned something troubling. Mathematics can describe worlds that may never be. It can conjure universes from pure logic, spin entire cosmologies from a single elegant formula. But elegance, my friends, is not the same as truth. There are those who say the equations of quantum mechanics demand the existence of parallel worlds, infinite copies of you and me, living out every possible choice, every unlived life, in realms forever beyond our reach. The mathematics, they insist, leaves no other option. And I must confess, the mathematics is beautiful. It is seductive in its completeness, its refusal to collapse into the single world we see around us. But beauty has led us astray before. I remember the debates with Bohr, those long nights arguing about whether the moon exists when no one looks at it. He believed reality itself is uncertain until observed, that the universe splits and branches with every measurement. I could not accept this. I still cannot. It offends something deep within me, this notion that nature plays dice, that reality fractures into infinite versions of itself simply because we chose to look. Yet here we are, decades later, and the question remains unanswered. The mathematics of quantum mechanics works flawlessly. It predicts the behavior of atoms with astonishing precision. But what it means, what it truly means, we do not know. We have learned to calculate, but we have not learned to understand. The parallel universe hypothesis is born from this confusion. It says, if every quantum possibility becomes real somewhere, then there must be countless versions of this universe, stacked like pages in an infinite book. In one universe you turned left instead of right. In another I never left Germany. In yet another, the stars themselves burn with different fire. It is a magnificent idea. It is also completely untestable. And this is where physics ends and speculation begins. Science is not just mathematics, it is measurement, it is prediction. It is the patient work of asking nature a question and listening for her answer. But these parallel worlds, if they exist, are forever sealed from us. We cannot visit them, we cannot measure them, we cannot even prove they are there. They exist only in the equations, like ghosts of possibility haunting the margins of our theories. I do not say this to dismiss the idea. I say it to remind us of our limits. We are pattern-seeking creatures, we humans. We find comfort in completeness, in explanations that tie every loose thread into a neat bundle. But the universe is under no obligation to satisfy our need for closure. Reality may be stranger than we can imagine, or simpler than we dare to hope. What troubles me most is not the mathematics, but the certainty with which some embrace it. They speak of parallel universes as if they were established fact, as if the equations alone were sufficient proof. But we have been here before. We have mistaken our models for reality, confused the map with the territory, and each time, nature has surprised us. Perhaps these other universes exist. Perhaps at every moment, reality branches into infinite possibilities. And somewhere another version of me sits in another office, writing different words. It is possible. But it is also possible that we are missing something fundamental, some deeper principle that would make sense of quantum mechanics without requiring an infinity of hidden worlds. I think often of Occam's razor, the principle that we should not multiply entities beyond necessity. If we can explain what we observe with one universe, why insist on infinite? Not because the mathematics forbids it, but because we lack the imagination to interpret it differently. This seems to me a failure of creativity, not a triumph of logic. And yet, I confess, there is something profoundly human in this yearning for parallel worlds. It speaks to our deepest hopes and regrets. It suggests that every choice we did not make is made somewhere, that every lost possibility is preserved in some distant reality. It offers a kind of cosmic forgiveness, the idea that all paths are taken, all lives lived, all loves found and lost in the vast multiplicity of existence. But I must ask, is this physics or is this philosophy? Is it science or is it consolation? The truth is, we do not know. And that is where we must begin, not with certainty, but with honest uncertainty. The universe may contain infinite copies of ourselves, or we may be alone in a single precious reality. Both possibilities are humbling. Both demand our respect. What I can tell you is this: the mathematics that hints at parallel universes is real. The questions it raises are legitimate, but the answers, the true answers, require more than equations. They require evidence. They require some way, however clever, to reach across the supposed boundary between worlds and test whether anything lies beyond. Until then, we stand at the edge of knowledge, peering into darkness. We can see the shapes our theories cast, the shadows on the wall of Plato's cave. But we must not mistake shadows for substance, possibility for proof. I have spent my life believing that the universe is comprehensible, that beneath its apparent chaos lies an order we can grasp. But comprehensible does not mean comfortable. The truth may be stranger than parallel universes, or more beautiful, or more terrible. It may be something we cannot yet even imagine. And so we must proceed with humility. We must follow the mathematics wherever it leads, but we must not forget that mathematics alone does not constitute reality. We must dream of other worlds, but we must not claim to know they exist. We must remain curious, skeptical, and above all, honest about what we know and what we merely hope. The question of parallel universes is not yet a question of physics. It is a question about the nature of existence itself, about the relationship between mathematics and reality, about the limits of human knowledge. And perhaps that is the most important lesson, that there are questions we can ask but not yet answer, mysteries we can approach but not yet solve. This does not diminish us, it ennobles us. It reminds us that the universe is larger than our theories, deeper than our equations, more wonderful than our most extravagant imaginings. And if there are other versions of me in other universes, I hope they have learned this too, that the search for truth requires not just intelligence, but wisdom, not just calculation, but wonder, not just answers, but the courage to live with questions. For in the end, it is not the certainty of knowledge that defines us, but the quality of our curiosity. And that, at least, requires no parallel universe to contain. Mathematics can describe worlds that don't exist. Beautiful equations and elegant formulas can conjure entire universes from pure logic, but mathematical possibility is not the same as physical reality. We must not confuse our models with truth itself. You know, when I was a young man, working in the patent office in Bern, I would spend my days examining the claims of inventors, people who believed they had discovered perpetual motion machines, or devices that could transmit messages faster than light, or mechanisms that violated the basic principles of thermodynamics. And what struck me was not their foolishness, but their sincerity. They had done the mathematics, they had drawn the diagrams. On paper, everything worked beautifully, the equations balanced, the gears meshed perfectly. And yet, when you built the machine, when you tried to make it exist in the actual world of wood and metal and sweat, it would not work. It could not work. Because the mathematics, however elegant, however internally consistent, was describing something that reality simply did not permit. This taught me something fundamental about the relationship between our minds and the universe. We are creatures who think in symbols, in numbers, in abstract patterns. We can write down equations that describe worlds we have never seen, universes that may never be. With a few scratches of chalk on a blackboard, I can conjure a cosmos where time runs backwards, where gravity repels instead of attracts, where light bends in impossible spirals. The mathematics will be perfect, every term will balance, every symmetry will hold, and yet none of it may correspond to anything real. This is both the power and the danger of mathematical thinking. Mathematics is a language of extraordinary precision and beauty. It allows us to see patterns that our eyes alone could never detect, to predict phenomena that our intuition would never guess. When I worked out the equations of general relativity, the mathematics told me that massive objects should bend the fabric of space itself, that light should curve around the sun, that time should slow near heavy bodies. These were absurd conclusions. They offended common sense. And yet, when the astronomers looked during the eclipse of 1919, there it was, starlight bending exactly as the equations predicted. The mathematics had described something true about reality. But here is what troubles me. Just because mathematics can describe reality does not mean that everything mathematics describes is real. This is a subtle distinction, but it is crucial. Mathematics is a tool, perhaps the finest tool we have for understanding nature, but it is not nature itself. It is our way of organizing our observations, of finding regularities in the chaos of experience, and like any tool, it can be misused. It can lead us to conclusions that are mathematically impeccable but physically meaningless. Consider the square root of -1, what we call an imaginary number. Mathematically, it is perfectly well defined. We can manipulate it, combine it with other numbers, use it to solve equations. And indeed, imaginary numbers turn out to be extraordinarily useful in describing quantum mechanics and electromagnetic waves. But does the square root of -1 exist in the same way that 3 apples exist, or the planet Jupiter exists? Of course not. It is a mathematical convenience, a symbol that helps us calculate, not a thing you could ever hold in your hand or point to in the sky. Now, you might say this is obvious, that no one would confuse a mathematical abstraction with a physical object. But I am not so sure. I have watched physicists, brilliant physicists, people whose mathematical abilities far exceed my own, become so enchanted by the elegance of their equations that they begin to believe the equations are more real than the reality they are supposed to describe. They fall in love with the map and forget about the territory. And this brings me to the question of parallel universes, these infinite copies of reality that some say must exist because the mathematics of quantum mechanics seems to require them. The argument goes like this. When we solve the equations that describe the behavior of particles, we find that they exist in what we call a superposition, a strange state where the particle is somehow in multiple places or multiple conditions at once. This is not a metaphor. The mathematics is clear. The particle is not here or there. It is, in some sense we do not fully understand, both here and there simultaneously. But then we observe the particle. We measure its position. And suddenly the superposition collapses. The particle is no longer in multiple states. It is in one definite location. The wave function, as we say, has collapsed. And this raises a disturbing question. What happened to all those other possibilities? Where did they go? One interpretation, the many worlds interpretation, says they did not go anywhere. They still exist, but in parallel universes that split off from ours at the moment of measurement. Every quantum possibility becomes real somewhere. Every path is taken. The universe branches endlessly, creating an infinity of worlds. Now, I must tell you, when I first encountered this idea, I thought it was madness. Not because it is impossible, I have learned never to say what is impossible, but because it seemed to me a kind of extravagant desperation, a refusal to admit that we simply do not understand what is happening. The mathematics works, yes, but does that mean the interpretation is correct? Does the fact that we can describe something mathematically mean that thing must exist? I think of the medieval astronomers who used epicycles to describe the motion of the planets. They would place circles upon circles upon circles, each one rotating at its own rate, and with enough epicycles, they could predict the positions of the planets with remarkable accuracy. The mathematics worked, but the epicycles themselves were not real. They were artifacts of a flawed model, a way of forcing observations to fit a theory that was fundamentally wrong about the structure of the solar system. When Kepler discovered that planets move in ellipses, not circles, all those epicycles vanished like morning mist. They had never been necessary. They were mathematical ghosts. And I genuinely wonder, whether these parallel universes might be the epicycles of our time, elegant mathematical structures that we have invented to make sense of observations we do not yet truly understand. Parallel universes cannot be tested. The many worlds interpretation may explain quantum mechanics mathematically, but if these other universes are forever beyond our reach and measurement, We've crossed from physics into speculation. Science requires evidence, not just equations. There is a principle in science, so fundamental that we sometimes forget to state it explicitly. If you cannot test an idea, if you cannot devise some experiment that might prove it wrong, then whatever you are doing, it is not quite science. It may be philosophy, it may be mathematics, it may even be poetry. But it is not science in the sense that Newton and Galileo would have recognized, not science as a conversation between human curiosity and nature's answers. I learned this lesson young, though not in any classroom. I learned it by asking myself silly questions, the kind of questions a child asks before the world teaches him to be serious. What would it be like to ride alongside a beam of light? If I could travel at the speed of light, what would I see? These were not respectable questions for a physicist. They were daydreams, thought experiments, the idle wanderings of an undisciplined mind. And yet, when I followed them far enough, when I asked what could actually be measured by someone moving at such speeds, I found my way to the theory of relativity. The daydreams became predictions, the predictions became experiments, and when the measurements were made, nature confirmed what the imagination had proposed. But here is the crucial part: it could have gone the other way. If the astronomers in 1919 had observed the eclipse and found that starlight did not bend around the sun, my beautiful equations would have been wrong. Elegantly wrong, perhaps, interestingly wrong, but wrong nonetheless. And I would have had to begin again, searching for a better description of gravity, one that matched what the universe actually does, rather than what I wanted it to do. This is the contract we make when we call ourselves scientists. We agree to let reality have the final word. Now, consider these parallel universes. These infinite copies of our world supposedly created every time a quantum measurement occurs. The mathematics that suggests them is impeccable. I do not dispute this. The equations of quantum mechanics, when taken at face value, seem to imply that reality branches endlessly, that every possible outcome of every quantum event becomes real in some universe somewhere. In one world, the electron spins up. In another, it spins down. Both universes are equally real, equally physical, equally filled with people like you and me who are utterly convinced theirs is the only universe. It is a spectacular idea. It has a certain grandeur to it, a kind of cosmic democracy where no possibility is ever wasted, where everything that can happen does happen somewhere. And I confess, there is something in me that wants to believe it, some aesthetic sense that finds it more satisfying than the alternative, that the universe simply collapses into one outcome and the others vanish like smoke for no reason at all. But here is my difficulty: how do we test it? How do we know? If these other universes exist, they are by definition beyond our reach. They split off from ours and can never interact with us again. We cannot visit them. We cannot send signals to them. We cannot detect them even in principle, because the moment they become separate universes, they cease to have any physical connection to ours. They are, in a very real sense, invisible, untouchable, unmeasurable. They exist, if they exist at all, in a realm that science cannot access. And this troubles me deeply, not because I am opposed to bold ideas. I have spent my life pursuing bold ideas. But because it seems to me we are abandoning the very thing that makes science powerful. We are saying, here is a theory that explains our observations, and it cannot be tested, and we should believe it anyway because the mathematics is beautiful. But beauty has deceived us before. The Ptolemaic system was beautiful. Aristotle's physics was beautiful. They were also wrong. You see, science is not just about finding explanations that fit the data. It is about finding explanations that can be checked, that make predictions we can verify or refute. When I said that gravity should bend light, that was a prediction. It could have been tested. It was tested. And if the test had failed, the theory would have been abandoned, no matter how beautiful the mathematics. This is what separates science from metaphysics, from theology, from pure speculation. Not that science is certain, it is not, but that science is answerable to evidence. But what evidence could possibly confirm or deny the existence of parallel universes? If they are truly separate from ours, if no information can pass between them, then by what means could we ever know they are there? It seems to me we are in the position of medieval scholars debating how many angels can dance on the head of a pin, a question that may be logically coherent, but is simply not the sort of question that observation can settle. Some will say, I am being too cautious, too conservative. They will point out that many things in physics were once thought to be unmeasurable, but later became accessible as our instruments improved. Perhaps, they say, we will someday find a way to detect these other universes, some clever experiment we cannot yet imagine. And I grant that this is possible. Science has surprised us before with its ingenuity. But I think there is a difference between something that is difficult to measure and something that is in principle unmeasurable. Atoms were difficult to observe directly, but they left traces, patterns in chemical reactions, tracks in cloud chambers, effects that could be detected. Parallel universes, as currently conceived, leave no traces at all. They are sealed off by the very theory that proposes them. And so I find myself in an uncomfortable position. I do not want to say the many worlds interpretation is wrong. How could I? I have no proof either way. But I also cannot say it is right, cannot treat it as established science, because we have no way of knowing. It exists in a strange liminal space between physics and philosophy, a place where our equations go but our instruments cannot follow. We must embrace honest uncertainty rather than claiming certainty about parallel universes based solely on mathematics. We should acknowledge what we don't know. The universe may be stranger than infinite worlds, or simpler. We simply haven't discovered the answer yet. There is a peculiar comfort in not knowing. I realize this sounds strange coming from someone who has spent his entire life trying to know, trying to understand, trying to pull back the curtain on nature's secrets. But I have learned, slowly, and sometimes painfully, that certainty is a dangerous drug. It makes us feel secure when perhaps we should feel wonder. It closes doors that ought to remain open. When people ask me about parallel universes, I notice they often want me to tell them yes or no. Does another version of me exist somewhere, making different choices, living a different life? It is a simple question. They expect a simple answer. But the universe, I have found, rarely offers us the simplicity we crave. More often, it offers us mystery wrapped in equations, patterns that hint at meaning without quite revealing it. And so I must say, I do not know. I genuinely do not know whether these infinite other worlds exist. The mathematics suggests they might. My intuition rebels against the idea. But neither mathematics nor intuition is a reliable guide to truth. They are tools, imperfect tools, wielded by imperfect minds, trying to make sense of something vast and strange. What troubles me is not the idea itself. I have entertained stranger ideas in my time, but the confidence with which some embrace it. They speak as if the question were settled, as if the equations alone were sufficient proof. And I want to say to them, wait. Slow down. Remember that we are limited creatures peering into an infinite cosmos. Remember that we have been wrong before, spectacularly wrong, even when we were certain we were right. The history of science is not a history of steady accumulation of truth. It is a history of revolutions, of fundamental assumptions overturned, of ideas that seemed absurd becoming commonplace, and ideas that seemed obvious, revealed as illusions. Newton thought space and time were absolute unchanging stages on which the cosmic drama unfolded. It seemed self-evident. It was wrong. We thought the universe was eternal and static. Common sense demanded it. Common sense was mistaken, and each time we discovered we were wrong, the universe became stranger, larger, more wondrous than we had imagined. Reality exceeded our theories. It always does. And this is why I distrust certainty, why I prefer the honest acknowledgement of ignorance to the false comfort of premature conclusions. When I say I do not know whether parallel universes exist, I am not being evasive. I am being precise. I am distinguishing between what we can demonstrate and what we can merely imagine, between the tested and the speculative, between science and its more adventurous cousin, philosophy. This distinction matters. It is perhaps the most important distinction we can make. But here is what I do know. The question itself is valuable. The wondering is valuable. Even if we never answer it definitively, the act of asking forces us to confront deeper issues about the nature of reality, about what it means for something to exist, about the relationship between mathematics and the physical world. These are not idle puzzles. They cut to the heart of what we are trying to do when we do science. And maybe, just maybe, the answer we seek is not a simple yes or no, but something more subtle, something that will require us to rethink our very concepts of existence and reality. Maybe the question of parallel universes is a signpost pointing toward territory we have not yet learned to map, ideas we do not yet have the language to express. Human yearning shapes our theories. The appeal of parallel universes speaks to our deepest hopes, that every unlived life exists somewhere, every choice is made. But we must ask, are we doing physics or seeking consolation? Truth requires separating what we wish from what we can prove. There is something deeply human about the idea of parallel universes, something that speaks not to our scientific minds, but to our hearts. When someone tells me that somewhere in another universe I made different choices, married a different woman, stayed in Europe instead of fleeing to America, became a violinist instead of a physicist, I feel something stir. Not conviction, but longing. A kind of bittersweet recognition of all the paths not taken, all the lives unlived. And I wonder sometimes if this is really what draws us to the many worlds interpretation. Not the mathematics. Most people cannot follow the mathematics, but the promise it seems to offer, the promise that nothing is truly lost, that every possibility is preserved somewhere, that the version of you who took the other job, who said yes instead of no, who turned left instead of right, still exists, still breathes, still matters in some distant cosmos you will never see. It is a beautiful thought. I do not mock it. We are creatures who live with regret, with the weight of roads not traveled. We wonder constantly about the life we might have lived if we had been braver, wiser, luckier. And here comes a theory that whispers, you did live that life. Somewhere, somehow, every version of you is real. It is a kind of cosmic forgiveness, is it not? A mathematical redemption. But I must ask, as gently as I can, is this physics or is this wish fulfillment? Are we following the evidence, or are we following our need for consolation? I do not mean to be cruel. I too have regrets. I too have wondered about the choices I made, the people I hurt, the opportunities I missed. There is a young patent clerk in Bern who had so many possible futures ahead of him, and sometimes I think of all the versions of that young man who never existed. The ones who gave up on physics, who stayed in Switzerland, who never dared to challenge Newton. And there is something appealing about imagining them living out their stories somewhere in the infinite branching of reality. But my desire for them to exist does not make them exist. My emotional attachment to an idea does not transform that idea into truth. This is perhaps the hardest lesson of science, that the universe does not care what we wish it to be. It simply is what it is, indifferent to our hopes and fears. And so I find myself suspicious when a scientific theory aligns too perfectly with human longing. Not because such alignment is impossible. Perhaps the universe really is structured in ways that comfort us, but because we must be especially careful in such cases. We must examine our motives. We must ask whether we believe something because the evidence compels us or because believing it makes us feel better. I have watched colleagues become attached to theories for reasons that had little to do with data. I have seen brilliant minds defend ideas long past the point of reasonableness, not from stubbornness, but from a kind of love. They had lived with these theories so long, had invested so much of themselves in them, that abandoning them felt like betrayal. And I understood this. I have felt it myself, but understanding it does not make it right. The question I keep returning to is this: if the many worlds interpretation were less emotionally satisfying, if it offered us no comfort about our unlived lives, would we still embrace it so readily? Or would we be more critical, more demanding of proof, more willing to say we simply do not know what quantum mechanics means? I think we would be more skeptical, and this troubles me. Not because scientists should be emotionless. We are human after all, with all the attachments and desires that implies. but because we must try to separate what we hope from what we know, what comforts us from what the evidence actually suggests. And so we arrive, as we often do in science, at the edge of knowing. Mathematics whispers of infinite worlds, our instruments remain silent. The equations are beautiful, the evidence is absent. Our hearts yearn for cosmic redemption, reality offers no such guarantees. I cannot tell you whether parallel universes exist, only that we do not yet have the means to know. What I can say with certainty is this: the universe we inhabit, this single, precious, mysterious reality, deserves our full attention, our deepest curiosity, our honest wonder. Perhaps that is enough. Perhaps it must be.